Tonight, we are going to ask how long a generation ship could actually survive in deep space. Picture a cylindrical vessel moving between the stars. Its outer hull is dark, except for rows of warm windows and the faint glow of radiator panels releasing heat into space. Far inside, the cylinder turns slowly around its central axis. That rotation presses people toward the inner surface and gives them something close to gravity. Along that curved interior are fields of wheat, potatoes, soybeans, and leafy vegetables growing beneath carefully controlled lights. Residential districts sit beside workshops and medical rooms. Children attend school while technicians inspect pumps, electrical systems, and the bearings that keep the habitat rotating. A person standing inside might see homes and trees curving upward in the distance, following the shape of the cylinder. Several thousand people could spend their entire lives in a place like this. In scientific and engineering discussions, such vessels are often called generation ships, world ships, or multi-generational interstellar vessels. Their defining feature is the length of the voyage. The people who leave Earth are not expected to reach the destination. Their children may never reach it either. Arrival belongs to descendants born decades or centuries after launch. Depending on the target and the speed of the vessel, the crossing could last roughly 100 years, 500 years, or more than 1,000 years. The original passengers would remember open skies, natural weather, and the place where the mission began. They would grow old inside the ship and pass responsibility to people who knew Earth only through recordings and stories. Each generation would inherit the same destination, along with every weakness built into the vessel before departure. By then, outside help would have little practical value. There would be no cargo ship carrying a new water filter. No nearby shipyard could replace a cracked structural beam. A failing reactor could not be removed and sent back to its manufacturer. If an unfamiliar disease appeared in the crops, the crew could not ship samples to thousands of laboratories and wait for specialists to solve the problem. Everything required for survival would already be aboard. That includes machinery, raw materials, seeds, medicines, diagnostic equipment, stored genetic material, technical archives, and the people trained to use them. The ship would need to repair worn systems, manufacture replacement parts, recycle waste, grow food, treat illness, and educate each new generation using only the resources contained within its hull. Humanity has kept spacecraft functioning for decades. Voyager 1 was launched from Cape Canaveral on September 5, 1977. Nearly half a century later, it remains the longest operating spacecraft ever sent into deep space. Voyager offers an extraordinary example of engineering endurance, yet it carries no farms, hospitals, factories, or human population. It does not recycle water for thousands of people. It does not maintain a breathable atmosphere or train new engineers after the original mission team is gone. Its remaining instruments can be switched off as its electrical power declines. A generation ship would not have that option for any system essential to life. This is why a vessel like this has no single expiration date. Its survival would depend on 7 clocks moving at different speeds. The power clock measures how long reactors, electrical converters, cooling equipment, and radiators remain usable. The machinery clock follows pumps, motors, bearings, valves, computers, and thousands of smaller components. The materials clock tracks fatigue in the hull, erosion of shielding, chemical breakdown, and the gradual loss of usable raw material. The ecological clock belongs to the closed systems recycling air, water, nutrients, and waste. The population health clock includes medicine, fertility, radiation exposure, and genetic diversity. The knowledge clock measures whether each generation can preserve the practical skills needed to understand and repair the ship. The final clock belongs to society itself. It measures whether the people aboard can maintain cooperation, legitimate government, and a reason to continue a mission chosen long before they were born. The vessel survives only while every essential clock still has time remaining. Its hull could remain sound while the farms begin losing reliable harvests. The reactors could continue producing electricity after the ship loses the precision tools needed to rebuild a failed pump. A healthy population could inherit detailed technical manuals while gradually losing the hands-on knowledge needed to use them. The machinery might still operate while the society surrounding it begins to fragment. A generation ship can appear warm, active, and stable, while one of those clocks is already approaching zero. So how long could such a world endure? Could it remain intact for 1 century? Could its systems be renewed for 5? Would anything recognizable as the original mission survive a voyage lasting 1,000 years? By the end of tonight, you are going to understand what keeps each clock moving, what causes it to accelerate, and which one is most likely to end the journey first. Before we continue, liking the video or subscribing helps this channel reach more people who enjoy calm journeys through the science of space. The clocks now have names. Measuring them begins with the distance ahead, because every extra year between stars gives each one more time to run down. From the outside, the generation ship is a warm cylinder surrounded by a distance almost impossible to picture. Its nearest possible destination would be Proxima Centauri, the closest known star beyond our own. Proxima lies about 4.24 light-years from Earth. A light-year is the distance light travels in 1 year, moving at nearly 300,000 kilometers every second. 1 light-year equals about 9.46 trillion kilometers. Even the closest star is therefore roughly 40 trillion kilometers away. Proxima Centauri belongs to a 3-star system. Its larger companions, Alpha Centauri A and Alpha Centauri B, lie about 4.37 light-years from Earth. They orbit each other while Proxima moves around the pair from much farther away. Proxima also has at least 1 confirmed planet, Proxima Centauri B, but its star produces powerful flares that may make the planet's surface difficult for life. A mission planner might prefer a more distant system with a calmer star or a wider selection of planets. Tau Ceti, a star somewhat similar to our own, is about 11.9 light-years away. The TRAPPIST-1 system lies close to 40 light-years from Earth and contains 7 known rocky planets, several of which orbit within the region where temperatures might allow liquid water under suitable atmospheric conditions. Each improvement in the destination can add centuries to the journey. Voyager 1 provides a useful measure of the gap between present spacecraft and interstellar travel. After its planetary encounters, it continued away from the solar system at roughly 17 kilometers per second relative to our star. At that speed, traveling the distance to Proxima Centauri would take around 74,000 years. Voyager would cross the entire span of recorded human civilization many times before arriving. Parker Solar Probe has moved much faster. During its closest approaches to our star, it has reached around 690,000 kilometers per hour, making it the fastest human-made object. That velocity comes from falling deep into the star's gravitational field while following a carefully shaped orbit. Parker cannot simply turn outward and preserve the same speed during a journey to another system. A true interstellar vessel would need its own propulsion system to accelerate a much larger mass and later slow it down. At 1% of light speed, roughly 3,000 kilometers per second, the cruise to Proxima Centauri would take about 424 years. This simple figure ignores the time required to accelerate, perform course corrections, and decelerate near the destination. At 5% of light speed, the same crossing falls to approximately 85 years. That begins to fit within one unusually long human lifetime, although the people who launched the vessel might still be elderly by arrival. The travel time to Tau Ceti at 1% of light speed would be around 1,190 years. Reaching TRAPPIST-1 at that speed would take close to 4,000 years. Propulsion proposals have tried to move those numbers into a more manageable range. Project Orion began in 1958. Its engineers studied a vessel propelled by repeated nuclear explosions behind a large metal pusher plate. Each explosion would strike the plate with a pulse of plasma, and a shock absorber system would transfer that push into the spacecraft. Orion could theoretically move extremely heavy payloads and might have reached a few percent of light speed in advanced versions. The design required large numbers of nuclear devices and raised severe engineering, political, and environmental problems. During the 1970s, the British Interplanetary Society developed Project Daedalus. Its proposed uncrewed probe would use pulses of nuclear fusion to reach Barnard's star, nearly 6 light-years away, in roughly 50 years. Daedalus was a serious engineering study, but it carried instruments rather than farms, hospitals, shielding, and thousands of people. The original design weighed tens of thousands of metric tons, with most of that mass devoted to fuel. A crewed world ship would be vastly heavier. Ideas such as warp drives and traversable wormholes offer much shorter journeys in theory. Warp drive models generally depend on regions of negative energy, a condition that has never been produced in the required form or quantity. Wormholes appear in some solutions to general relativity, yet no traversable wormhole has ever been observed, and keeping one open may demand forms of matter or energy that remain unknown. Known physics leaves the ship traveling below light speed. This fixes the duration of every survival clock introduced earlier. A faster ship faces greater energy demands and more violent impacts with interstellar dust. A slower vessel eases some propulsion requirements while exposing its machinery, ecosystem, population, and institutions to centuries of additional wear. Once the crossing becomes longer than a human life, passengers are no longer enough. The vessel must carry the systems, knowledge, labor, and productive capacity of an entire civilization. Morning aboard the ship would begin quietly. Lights in the residential districts would brighten according to an artificial day and night cycle. Families would eat food harvested from agricultural decks only a few kilometers away. Children would move through school corridors, while technicians began another shift in the water plant, the power station, or the machine shops surrounding the central axis. Elsewhere, a physician might examine a broken wrist. A biologist could test a crop for fungal infection. Engineers would compare vibration readings from a cooling pump with measurements recorded the previous month. None of these jobs would be temporary support for a voyage. Together, they would form the ordinary economy of the vessel. A generation ship carrying 1,000 people would need several physicians because illness, surgery, childbirth, and dental care would continue throughout the crossing. Engineers would be divided among power, propulsion, structures, electronics, life support, and manufacturing. Farmers and biologists would manage crops, microorganisms, water chemistry, and animal populations. Machinists would produce replacement parts. Teachers would prepare children to take over all of those roles before the current specialists grew old. A community of 1,000 would still have narrow limits. Earth distributes rare expertise across billions of people and thousands of universities, hospitals, laboratories, and factories. A generation ship might have only one person with deep experience in a particular reactor component or plant disease. The loss of that individual could remove a skill the vessel would later need. Larger populations reduce some of that danger. They allow more specialists, broader genetic diversity, and additional workers during emergencies. They also require more farmland, housing, water, electrical power, medical capacity, and shielding. Every extra passenger increases the mass that must be accelerated toward another star and slowed again near arrival. The physical scale grows rapidly. The International Space Station has a mass of roughly 420 metric tons. It supports a small rotating crew, receives regular cargo deliveries, and depends on thousands of people working from Earth. Its pressurized living volume is comparable to a large house, spread through connected modules. Project Daedalus, the uncrewed fusion probe study developed during the 1970s, was estimated to weigh about 54,000 metric tons. Most of that mass consisted of propellant. Daedalus carried scientific instruments rather than apartment districts, hospitals, farms, or radiation shelters. A crewed world ship could weigh hundreds of thousands or several million metric tons. Its exact mass would depend on population, speed, shielding thickness, agricultural area, propulsion, and the amount of industrial equipment carried aboard. Water alone would account for an enormous quantity of material because it would serve drinking, farming, cooling, and radiation protection. That mass cannot be devoted entirely to stored supplies. A warehouse filled with food offers a temporary reserve. Even a supply lasting 50 years would be exhausted long before many generation ship voyages ended. Farms create new food from light, carbon dioxide, water, and recycled nutrients. Stored oxygen also has a finite limit. While biological and mechanical systems can continually recover it from carbon dioxide and water, the same principle applies to equipment. A room filled with spare pumps can solve failures until the final pump is installed. A functioning machine shop can produce new housings, shafts, brackets, and valves from recycled metal. Chemical equipment can recover useful substances from waste. Damaged components can be melted, separated, tested, and formed into new material. These processes are productive loops. Waste becomes a source of nutrients or raw material. Water moves through people, crops, treatment systems, and storage tanks before returning for use. Metals travel from worn machinery into furnaces and eventually return as replacement parts. Every loop depends on the others. Farms require lighting and pumps. Power systems require cooling. Cooling requires water. Water treatment requires filters and manufactured components. The factories producing those components need energy and trained operators. Project Hyperion, an interdisciplinary world ship design effort announced in the mid-2020s, treated this vessel as a combined engineering and social problem. Its design challenge brought together architecture, ecological planning, sociology, and technical systems for a voyage lasting roughly 250 years. That approach reflects the true scale of the task. A successful design must provide living space while also preserving the institutions that operate it. The ship has now become something larger than a spacecraft. It is an artificial country with a finite territory, a closed material supply, and no neighboring economy to absorb a shortage. Its population could recycle matter, rebuild machinery, and train new specialists for centuries. Human bodies would still need an environment that allows them to remain healthy through pregnancy, childhood, adulthood, and old age. The most immediate missing condition would be the steady pull of gravity. For the people living inside the vessel, gravity would shape nearly every part of daily life. Adult astronauts already show how quickly the human body responds when gravity disappears. During long stays in orbit, Bones lose mineral because they no longer carry normal weight. Muscles in the legs and back weaken from reduced use. The heart works differently because it no longer needs to pump blood upward against gravity, and fluids shift toward the head. These changes can begin within weeks. Astronauts aboard the International Space Station spend roughly 2 hours exercising each day. They use a treadmill with straps holding them down, a stationary bicycle, and a resistance machine that imitates weightlifting. This slows the loss of bone and muscle, though it does not reproduce every effect of living on Earth. A generation ship would face a much wider problem. Its passengers would remain away from natural gravity throughout pregnancy, infancy, childhood, and old age. No human pregnancy has ever been carried to term in sustained microgravity. Researchers therefore do not know how a fetus would develop without a steady downward force. Gravity influences the growth of bones, muscles, the inner ear, and the cardiovascular system. It also guides movement before birth, as the developing body responds to pressure and orientation. Experiments involving mice, fish, and other animals have revealed changes during development in low gravity, but those studies cannot tell us whether generations of humans could grow normally under the same conditions. The most practical solution allowed by known physics is rotation. Imagine the inhabited cylinder turning around a long central axis. A person standing on the inner wall moves in a circle. Their body naturally wants to continue traveling in a straight line, while the curved floor continually redirects that motion. The floor presses against their feet, creating the sensation of weight. This effect is commonly called centrifugal force from the passenger's point of view. The actual physical process is centripetal acceleration, meaning acceleration directed toward the center of the rotating structure. The strength of the apparent gravity depends on the size of the cylinder and how quickly it turns. At 1 rotation per minute, a habitat needs a radius of roughly 900 meters to create something close to Earth's gravity at the floor. The full cylinder would therefore measure about 1.8 kilometers across. At 2 rotations per minute, the required radius falls to around 225 meters. That makes the structure much smaller, though faster rotation produces stronger Coriolis effects. The Coriolis effect becomes noticeable when a person moves through a rotating environment. Walking toward the central axis, climbing a ladder, or turning the head quickly can create unexpected sideways sensations. The inner ear may interpret those movements as spinning or tilting, causing dizziness and nausea. Larger habitats reduce this problem because they can rotate more slowly. They also reduce the difference between the apparent gravity at a person's feet and head. Inside a small rotating room, the feet might experience a noticeably stronger pull because they are farther from the axis. In a cylinder hundreds of meters wide, that difference becomes much smaller. Large rotating habitats were studied in detail during the 1970s. Physicist Gerard O'Neill proposed enormous cylinders for permanent settlements in space. Some versions were several kilometers long and contained farmland, homes, lakes, and broad interior landscapes. His designs were intended mainly for orbit around Earth or the home star, yet the same geometry appears in many generation ship concepts. Rotation gives the population a familiar floor and allows water to remain in containers. Crops can grow with roots oriented downward, while dust and loose objects settle instead of floating through ventilation systems. The structure pays a mechanical price for that comfort. At 1 rotation per minute, the cylinder completes 525,600 revolutions each year. Over 500 years, it turns more than 260 million times. The outer walls remain under constant tension because every section of the habitat is trying to move outward. Agricultural soil, water tanks, buildings, machinery, and people all add to that load. Slight imbalances in mass can produce vibration. Moving heavy equipment between districts can shift the vessel's center of mass, requiring careful control. The hull must tolerate repeated stress, while radiation alters materials and microscopic cracks slowly grow. Motors may be needed to adjust rotation. Bearings or magnetic supports around internal structures require inspection. Sensors must track vibration, alignment, and strain for centuries. Inside, the gravity would feel calm and ordinary. A cup would remain on a table. Children could run across a curved park, while trees grew toward the floor beneath them. Every quiet moment would depend on a world-sized machine continuing to turn. Keeping that machine rotating while farms remain illuminated, rooms stay warm, and air moves through the habitat requires a steady supply of power. A generation ship would wake each morning only because electricity had already been moving through it for hours. Fresh air would pass through fans and carbon dioxide scrubbers. Pumps would push water through filters, storage tanks, and agricultural pipes. Lamps above the crops would switch on according to carefully timed growing cycles. Medical scanners, laboratory instruments, navigation computers, and machine tools would all draw power from the same electrical network. Even a simple breakfast would depend on that network. Electricity would illuminate the plants that produce the food, move nutrient-rich water around their roots, regulate temperature, and return moisture from the air to the water system. A surgical procedure would require sterilization equipment, lighting, ventilation, monitoring devices, and a controlled supply of oxygen. Power would sit beneath almost every other survival system. Solar panels could help near the beginning and end of the journey, while the vessel remained close to a star. Their usefulness would fall rapidly as the ship moved outward. Light intensity follows the inverse square law. This means that doubling the distance reduces the available light to 1/4. At 5 times the distance, the panels receive only 1/25 as much energy. Between stars, the nearest useful source of light could be several light years away. Solar power would contribute almost nothing during most of the crossing. The ship would need to carry its main energy source. Nuclear fission offers the most mature, high-density option currently available. Inside a fission reactor, the nucleus of a heavy atom such as uranium splits into smaller pieces. That reaction releases heat and additional neutrons, which can split more atoms in a controlled chain reaction. The heat warms a coolant. The coolant carries energy into turbines or other power conversion equipment. Generators then turn that mechanical or thermal energy into electricity for the ship. Naval reactors show how long a compact reactor can operate. Some modern submarines and aircraft carriers use reactor cores designed to last for decades without refueling. Those vessels still receive regular inspection, skilled maintenance, replacement components, and support from large industrial systems on land. Commercial power reactors also have operating lives measured in decades. Many were originally licensed for about 40 years, with some later receiving extensions after extensive inspection and refurbishment. None were designed to work unattended for 500 years. Fuel life therefore tells only part of the story. A reactor may still contain usable uranium while its coolant pumps begin to fail. Valves can leak. Control mechanisms can seize. Sensors can drift away from accurate readings. Neutrons striking the reactor vessel can gradually alter the metal and make it more brittle. Fuel cladding, which forms a protective layer around the nuclear fuel, can crack or corrode. Turbines, generators, electrical converters, and cooling equipment all have separate operating limits. Keeping one reactor alive for centuries may require replacing nearly everything around its fuel several times. A breeder reactor could extend the fuel supply. This type of reactor converts material that does not readily split, known as fertile material, into new fissile fuel that can support a chain reaction. Uranium-238, for example, can eventually be converted into plutonium-239. That process can extract far more energy from a limited fuel supply. It also requires additional chemical processing, radiation shielding, control equipment, and specialist knowledge. Each added capability creates more machinery that must remain serviceable. Fusion could offer even greater energy density by combining light atomic nuclei. Project Daedalus relied on fusion pulses for propulsion, and many generation ship concepts assume that controlled fusion will eventually provide onboard power. Humanity has produced fusion reactions in laboratories, yet no compact fusion plant currently generates dependable electrical power for a spacecraft. A system capable of operating for centuries would demand another large leap beyond that. Radioisotope generators offer a simpler option for smaller loads. These devices collect heat from radioactive decay and contain few moving parts. Voyager 1 uses this general type of power source. Its plutonium-238 has a half-life of about 87.7 years, meaning half of the original isotope remains after that time. The electrical output declines gradually as the material decays and the conversion equipment ages. No matter which source is chosen, every watt used inside the ship eventually becomes heat. Computers warm their surroundings. Lamps heat the farms. Motors release heat through friction and electrical resistance. Human bodies also add thermal energy to the habitat. On Earth, heat can move into air, water, soil, and the wider environment. In deep space, the ship must release it as infrared radiation from large external panels called radiators. Their size depends on how much heat must be removed and how hot the panels are allowed to become. Radiators must face open space. Thick armor would trap the heat they are meant to release, so these surfaces remain exposed to dust impacts, radiation, and mechanical damage. The power system therefore forms a continuous chain. Fuel produces heat. Conversion machinery creates electricity. Electrical systems keep the civilization alive. Radiators carry the remaining heat away. A failure anywhere along that path reduces the power available everywhere else. The first visible sign might be dimmer agricultural lighting or warmer rooms. Soon afterward, water processing slows, cooling weakens, and air circulation becomes harder to maintain. Even a ship carrying centuries of nuclear fuel would still depend on machinery capable of converting that fuel into life. Around each reactor would be thousands of smaller machines performing quieter work. Coolant pumps would move heat away from the core. Valves would regulate pressure. Motors would turn fans. Agricultural equipment, machine tools, and water treatment systems. Sensors would measure temperature, vibration, radiation, flow rate, voltage, and chemical composition. Each device would contain several parts capable of failing in different ways. A pump may look like one object from the outside, yet its operation depends on a shaft, bearings, seals, an impeller, a motor, wiring, and control electronics. The seal may lose elasticity and begin leaking while the motor remains healthy. A bearing can develop a rough surface that increases vibration. The impeller can erode as particles pass through the fluid. Electrical insulation may crack after years of heat and radiation exposure. Careful construction slows these processes. It cannot remove them completely. Metals experience fatigue when repeated loads allow microscopic cracks to grow. The load may remain far below the force needed to break a new component. Millions of cycles can gradually extend a crack until the remaining metal can no longer carry the stress. Aircraft wings, bridges, pressure vessels, and rotating machinery are all designed with fatigue in mind. Engineers estimate how many cycles a part should survive and inspect critical areas before damage reaches a dangerous size. A generation ship would continue accumulating cycles for several human lifetimes. The rotating habitat alone might complete more than 500,000 revolutions each year. Pumps could turn millions of times in a few days. Valves in atmospheric and water systems might open and close several times each hour. Small changes in alignment or vibration would matter because they could reveal a defect long before a visible failure appeared. Non-metal materials would age as well. Polymers are long-chain molecules used in seals, cable insulation, hoses, coatings, and countless flexible parts. Heat and radiation can break or rearrange those molecular chains. A soft seal may gradually harden. A hose can lose flexibility and develop cracks. Some plastics release trapped gases in vacuum, a process called outgassing, which can contaminate optical equipment and sensitive surfaces. Lubricants also change with time. Oils can oxidize when they react with oxygen. Different ingredients may separate during long storage. Lighter compounds can evaporate. Dust, metal fragments, or chemical contaminants can enter a bearing and turn the lubricant into an abrasive mixture. Electrical equipment carries its own slow forms of decline. Contacts can corrode or build resistance, creating unwanted heat. Solder joints can crack after repeated heating and cooling. Some tin-based coatings grow extremely thin metal filaments called tin whiskers. These whiskers may extend across a gap between electrical conductors and cause a short circuit. Radiation can upset electronics in a fraction of a second. A high-energy particle passing through a computer chip may change a stored bit of information, producing what engineers call a single-event upset. Redundant computers and error-correcting memory can detect many of these events. Long-term radiation exposure creates permanent damage as atoms inside semiconductor materials are displaced from their normal positions. Over many years, a sensor or processor may become less accurate, consume more power, or stop functioning. Even healthy sensors drift. A pressure gauge that once measured perfectly may begin reporting a value slightly too high. Calibration compares the instrument with a known standard and corrects the difference. The standards themselves must remain accurate, creating another chain of equipment that needs inspection. A generation ship would rely heavily on preventive maintenance. Technicians would search for defects while systems were still operating. Ultrasonic testing sends high-frequency sound through metal and listens for echoes from hidden cracks. Radiography uses penetrating radiation to reveal flaws inside welds and pressure vessels. Vibration analysis compares the movement of a pump or motor with its normal pattern. Thermal cameras can identify an electrical connection becoming unusually hot. Acoustic sensors may detect the faint sound released as a crack grows. These methods allow crews to replace a part during planned maintenance, instead of waiting for it to break during an emergency. Reliability is often described using mean time between failures. This figure estimates the average operating time between one failure and the next for a repairable component. A pump with a long expected life may be highly dependable on its own. The ship would contain thousands or perhaps millions of repairable items. Even when individual components fail rarely, the total population of machines guarantees that something will need attention almost every day. Age would slowly change the balance. Original components would disappear. Replacements would begin accumulating their own wear. Inspection teams would spend more time watching old systems, while unexpected failures consumed labor that had been assigned elsewhere. A component capable of working for 50 years sounds exceptionally durable. During a 500-year journey, the ship would still need to replace it roughly 10 times. Each replacement requires a suitable part, trained workers, functioning tools, and enough time to complete the repair safely. The machinery clock remains manageable while maintenance can find and correct damage faster than new damage appears. That advantage depends on the ship continuing to produce every seal, bearing, circuit, and precision component it consumes. A coolant pump fails in the agricultural district during the ship's 187th year. The fault is ordinary. A bearing has worn unevenly, allowing the shaft to vibrate. The impeller now brushes against its housing, reducing the flow of water through several crop beds. Earlier generations replaced this model from a store of identical spares. The last packaged unit was installed 12 years ago. Technicians carry the damaged pump into the manufacturing district and begin working backward from the part they need. The new shaft must have the correct diameter, surface hardness, and alignment. A lathe can rotate a metal bar while a cutting tool removes material with controlled precision. Milling machines shape flat surfaces, slots, and complex housings. Furnaces melt scrap metal or heat-finished components, so their internal structure develops the required strength. Measurement is as important as shaping. A shaft, only a fraction of a millimeter too wide, may seize when it warms. One made slightly too narrow can vibrate and damage its seals. Micrometers, laser gauges, and reference blocks allow machinists to compare a new component with the dimensions stored in the ship's technical archive. The metal itself must also be understood. Stainless steel contains iron combined with carefully controlled amounts of chromium, carbon, nickel, and other elements. Chromium helps form a thin, protective layer that resists corrosion. Melting several worn components together can change those proportions. Paint, lubricants, solder, and fragments of other alloys may introduce contamination. Repeated recycling, therefore, requires chemical analysis. Spectrometers can identify elements by studying the light produced or absorbed by a sample. Refining equipment may remove unwanted material, while fresh alloying elements restore the desired composition. Every test consumes energy and depends on calibrated instruments. The cutting tools have their own lifetimes. Modern machine shops often use inserts made from tungsten carbide or hard ceramics. Their edges gradually chip and wear under heat and pressure. Coolant carries heat away from the workpiece, yet pumps must circulate it. Filters must remove metal particles, and chemical additives must remain available. Bearings inside the lathe eventually need replacement. Motors age, position sensors drift. Computer controls depend on power supplies and circuit boards. The problem becomes recursive, because the machines rebuilding the ship must also be rebuilt. Additive manufacturing can reduce some of this burden. A printer can build a component layer by layer, creating internal channels or shapes that would be difficult to machine. Metal printing still requires controlled powder, heat treatment, inspection, and often final machining. Printed parts may contain tiny pores or uneven internal stresses that reduce fatigue life. Some materials remain much harder to reproduce. A semiconductor chip begins with extremely pure silicon. Manufacturing advanced electronics requires clean rooms, carefully controlled gases, chemical baths, precision optics, and equipment able to create features far smaller than a human hair. Earth's semiconductor industry spreads that work across specialized companies and enormous factories. A generation ship may carry protected stocks of processors, sensors, memory, and power electronics, while producing simpler mechanical components aboard. Over several centuries, even stored electronics face radiation damage, corrosion, and failures in packaging materials. Design choices made before launch would determine how long those reserves last. Standardized bolts, seals, motors, and electrical connectors reduce the number of unique items the factory must support. Modular equipment allows one unit to be removed without dismantling an entire system. Inspectable housings and replaceable subassemblies preserve options that sealed disposable machines would remove. Project Hyperion and other world-ship studies place manufacturing near the center of survival planning for this reason. Productive capacity extends the vessel's life more effectively than warehouses alone. When shortages appear, the crew can begin cannibalizing less essential areas. Parts from an unused recreation hall might keep a water plant operating. Electronics removed from a retired laboratory could repair a navigation computer. Empty residential sections may become sources of wiring, glass, structural metal, and insulation. This process can continue for a long time, though each sacrifice narrows what the civilization can still do. A later generation may inherit machine tools with wider tolerances, fewer working sensors, and a smaller library of usable materials. The decline could remain gradual enough to feel normal. The factory survives, while it can reproduce the tools, precision, and knowledge required for its own renewal. Recycling can recover much of the metal and water still aboard, but material vaporized from the forward shield is already gone. Beyond the forward shield, interstellar space contains a thin mixture of gas, plasma, magnetic fields, and dust. Most of its matter is hydrogen. In the region surrounding our solar system, the density may fall below 1 atom per cubic centimeter. A cubic centimeter is about the volume of a small sugar cube, so the ship would often cross spaces containing less than a single atom within that volume. This sounds almost perfectly empty. At interstellar speed, even such sparse material arrives continuously. Individual hydrogen atoms strike the forward surface first. Some are electrically charged and can be influenced by magnetic or electric fields. Others are neutral and continue directly into the shielding. Each atom carries very little mass, though trillions of impacts gradually heat, erode, and alter exposed materials. Dust creates a more concentrated danger. Interstellar dust includes tiny grains of silicate minerals, carbon-rich material, metals, and frozen compounds. Many grains are smaller than smoke particles. A grain measuring only 1 microgram has a mass of 1/1,000,000th of a gram. Resting on a table, it would be invisible without magnification. At 1% of light speed, that grain would strike the ship at nearly 3,000 kilometers per second. Its kinetic energy would be about 4,500 joules. That is comparable to the energy carried by a fast rifle projectile, concentrated into a particle far smaller than a grain of sand. At 3% of light speed, the same 1 microgram grain carries roughly 40,000 joules. Increasing the speed by a factor of 3 increases the energy by a factor of 9. A 1 milligram particle is still tiny, weighing about as much as a small speck of dust. At 3% of light speed, it carries approximately 40 million joules of kinetic energy. These speeds remain low enough for the familiar kinetic energy equation to provide a close estimate. The equation uses 1/2 of the mass, multiplied by the speed squared. Relativistic corrections, which account for the more unusual behavior of objects approaching light speed, remain fairly small at 1 or 3%. The squared speed is the important part. Doubling the ship's velocity cuts the cruise time roughly in half, while making every collision about 4 times more energetic. An impact at thousands of kilometers per second does not leave an ordinary dent. The grain and part of the shield are heated so rapidly that they vaporize. Atoms lose electrons, producing an expanding cloud of electrically charged gas called plasma. That plasma can drive a shock wave into deeper layers and scatter hot fragments across a wider area. The leading end of the ship would therefore require several layers of protection. A Whipple shield uses a relatively thin outer plate placed some distance ahead of the main hull. When a small projectile strikes the first layer, it breaks apart and spreads into a cloud. The wider cloud reaches the deeper shield, with its energy distributed across a larger area. Modern spacecraft already use versions of this design against orbital debris and natural micrometeoroids. A generation ship would need a much thicker and more complicated system because its collision speeds could be hundreds of times greater. Several sacrificial plates could be arranged in sequence. Water tanks or blocks of ice might sit behind them, combining impact protection with radiation shielding and useful storage. Dense reserves of raw material could also be positioned toward the front, allowing cargo to protect the inhabited regions. Each layer would slowly erode. The factory districts would need to inspect the shield, move replacement material forward, and rebuild damaged sections without exposing the habitat behind them. Repair robots could work outside, though their joints, cameras, cables, and tools would face the same stream of impacts. Electromagnetic fields might redirect charged atoms and plasma before they reached the hull. Neutral dust grains would pass through those fields unless they were first charged by lasers or other equipment, adding another active system that would need continuous power. Some interstellar studies have proposed releasing a cloud of fine material ahead of the ship. The cloud would move with the vessel and absorb incoming dust before it reached the main shield. Keeping that buffer correctly positioned over millions of kilometers would require continual replenishment and precise navigation. Larger objects would need to be detected far in advance. Telescopes or radar could identify some approaching fragments and allow small course changes. The smallest grains may remain too faint and numerous to track individually, leaving the shield to absorb them. The ship could cross an almost empty region for centuries and still lose material from its oldest surface every day. Greater speed shortens the period of exposure, yet it makes each impact more severe. Dust can be broken apart, absorbed, or diverted. The highest energy particles traveling through deep space are far harder to stop, and some will continue through the shielding into the living world behind it. Beyond the worn outer shielding, energetic particles continue inward. Some radiation near a star comes from flares and other bursts of activity. Those events can release large numbers of protons over hours or days. A ship can respond by moving people into heavily protected shelters until the storm passes. Galactic cosmic rays create a different problem. They arrive continuously from outside the local star system, accelerated by violent processes such as supernova remnants. Their energies can be so high that magnetic fields and ordinary layers of metal provide only limited protection. Most galactic cosmic rays are protons, the positively charged particles found inside atomic nuclei. A smaller fraction consists of heavier nuclei, including carbon, oxygen, silicon, and iron. These heavy ions carry more charge and can leave dense trails of damage as they pass through tissue. The damage begins through ionization. A fast particle transfers enough energy to knock electrons away from atoms and molecules. That process can break chemical bonds, alter proteins, and damage the strands of deoxyribonucleic acid that carry genetic instructions inside cells. Cells can repair many ordinary breaks in their genetic material. Cosmic radiation may create several breaks and chemical changes within a tiny region. This clustered damage is harder to repair accurately because several pieces of the molecule have been disturbed at once. An incorrect repair can kill the cell or leave behind a mutation. Most mutations cause no lasting harm. Some can interfere with the systems controlling cell growth and increase the chance of cancer years later. Heavy ions may also affect the central nervous system. Laboratory studies suggest that radiation can alter neurons, supporting cells and blood vessels in the brain. Researchers continue investigating possible effects on memory, attention, coordination, and long-term cognitive health. Radiation is treated as one of the central hazards of human travel beyond Earth's protective magnetic field. A generation ship would face that environment for centuries rather than months. More shielding lowers exposure, although the relationship is complicated. Water is useful because it contains large amounts of hydrogen. Polyethylene, a common plastic made mostly from carbon and hydrogen, can also slow charged particles while producing fewer harmful fragments than some heavy metals. A generation ship could place water tanks around sleeping areas. Food stores, waste containers, and hydrogen-rich structural materials could surround hospitals and residential districts. Medical rooms and nurseries might sit deep inside the habitat, where several layers of machinery and stored material provide additional protection. Very heavy shielding can create secondary radiation. When an energetic cosmic ray strikes a metal nucleus, the collision may break that nucleus apart. Neutrons and smaller nuclear fragments then continue into the ship. These secondary particles can deposit radiation in areas that the original cosmic ray might not have reached in the same way. Engineers would therefore combine different materials and thicknesses, rather than relying on one massive metal wall. Shielding could reduce the average dose while recognizing that the most energetic particles may still penetrate deeply. Exposure would vary throughout the vessel. Work areas near the outer hull or forward shield might receive higher doses than protected residential zones. Crews could rotate through those locations so the same people did not accumulate the greatest exposure year after year. Personal dosimeters would record the radiation received by each person. Fixed detectors could map conditions across the habitat. Doctors would compare lifetime exposure with blood tests, imaging, neurological examinations, and cancer screening. The biological concern extends beyond the adults currently working aboard. Sperm cells and developing eggs can carry radiation damage into reproduction. Embryos and fetuses contain rapidly dividing cells that may respond differently from mature adult tissue. Children have many decades of life ahead of them, leaving more time for radiation-related diseases to develop. Stored sperm, eggs, embryos, seeds, and tissue cultures would need protected locations of their own. Several copies could be kept in separate compartments, so one accident or cooling failure did not destroy the entire genetic reserve. Radiation would become part of the ship's permanent climate. Its intensity would be measured like temperature or air pressure, then included in decisions about work schedules, pregnancy, medical care, and habitat design. The people inside could feel ordinary gravity beneath their feet and breathe comfortably while invisible particles continued passing through the walls around them. Their effects may unfold over years. The atmosphere surrounding the population must remain safe every hour. Inside the protected habitat, every breath changes the atmosphere by a tiny amount. An adult resting quietly draws oxygen into the lungs, where it passes into the blood. Cells use that oxygen to release energy from food, producing carbon dioxide as a waste product. The carbon dioxide returns through the bloodstream and leaves the body with the next breath. Across a population of several thousand people, this exchange continues every second. Oxygen concentration slowly falls, while carbon dioxide rises, unless the ship actively reverses the process. Stored tanks could provide an emergency reserve, but carrying centuries of breathing gas would add an impossible amount of mass. The atmosphere must be renewed continuously. Mechanical systems can perform much of that work. Carbon dioxide scrubbers pass cabin air through materials that selectively capture the gas. Some systems use replaceable chemicals. Regenerative scrubbers release the captured carbon dioxide when heated or exposed to vacuum, allowing the same material to be used again. Oxygen can be recovered from water through electrolysis. Electricity splits water molecules into hydrogen and oxygen. The oxygen returns to the habitat, while the hydrogen can be stored, used in chemical reactions, or combined with captured carbon dioxide to recover additional water. Every step depends on pumps, valves, electrical power, sensors, and carefully controlled chemistry. Plants add a biological route. During photosynthesis, leaves absorb carbon dioxide and use light energy to build sugars, releasing oxygen. Algae can perform the same basic process inside tanks or transparent tubes. This creates the appealing image of a ship whose farms provide both food and breathable air. The balance is more complicated than it appears. Plants also respire. Their cells consume oxygen to release usable energy from stored sugars, especially when the lights are off. Roots respire continuously. Bacteria and fungi living around those roots consume oxygen as they break down organic matter. A field may produce more oxygen than it uses during active growth. After harvest, the balance changes. Dead leaves and roots enter the waste system, where microorganisms consume oxygen while decomposing them. A crop disease, lighting failure, or change in planting area can alter the atmosphere along with the food supply. Biosphere. 2 demonstrated how strongly these hidden processes can affect a closed habitat. Its first sealed mission began in Arizona in September of 1991. 8 people entered a glass-covered structure occupying about 3.14 acres. Inside were designed environments that included a rainforest, a small ocean, agricultural areas, and a desert. The original atmosphere contained close to 21% oxygen, similar to outdoor air. Over the following months, that concentration steadily declined. It eventually reached approximately 14.2%, a level similar to breathing at an altitude of around 3,000 meters. The residents became tired more easily. Some experienced sleep problems and reduced physical ability. Much of the missing oxygen had been consumed by microorganisms in the unusually rich agricultural soil. The microbes broke down organic material faster than designers expected. Carbon dioxide produced during that process did not remain entirely in the air because exposed concrete absorbed some of it through chemical reactions. The result was difficult to recognize at first. Oxygen was disappearing, yet the expected rise in atmospheric carbon dioxide was partly hidden inside the building materials. Supplemental oxygen was eventually added. Other ecological changes unfolded at the same time. Many introduced animal species declined or disappeared. Pollinating insects were lost, while certain ants, cockroaches, and fast-growing vines became unusually successful. A system designed from known species and measured inputs still developed in unexpected directions. A generation ship would require far tighter control and far greater redundancy. Sensors would continuously measure oxygen, carbon dioxide, humidity, pressure, and trace gases. Reserve tanks could stabilize the atmosphere during crop failures or equipment repairs. Mechanical scrubbers would operate beside biological systems, so neither carried the entire burden. Too little oxygen reduces physical and mental performance before it becomes immediately fatal. Excess oxygen creates a different danger by allowing fires to ignite more easily and burn more intensely. Elevated carbon dioxide can cause headaches, impaired concentration, and sleep disturbance at levels well below those that stop breathing. The atmosphere may feel ordinary, while its chemistry is slowly moving away from safety. Maintaining it requires constant measurement, adjustment, and biological understanding. Every breath also connects the air system to water. Moisture leaves the body through breath and sweat, enters crops through their roots, and returns through filters that must recover the same limited supply again and again. A glass of water aboard the ship might begin in a storage tank deep inside the hull. A pump sends it through a final purification stage before it reaches a drinking tap. After someone drinks it, part of that water enters the bloodstream, moves through cells, and eventually leaves the body through urine, sweat, breath, or waste. Moisture from the lungs enters the cabin air with every exhalation. Sweat evaporates from the skin and is collected by humidity control equipment. Urine flows into a separate treatment system. Water used for washing, food preparation, and medical care creates additional streams with different contaminants. The ship's farms produce an even larger flow. Water enters plant roots, travels through stems, and evaporates from tiny openings in the leaves. This process is called transpiration. Much of that moisture returns to the air and can be condensed again. The remainder stays temporarily inside crops, nutrient solutions, harvested food, roots, and plant waste. Each stream requires a different form of treatment. Urine contains water mixed with salts, urea, medications, and metabolic waste. Hygiene water may carry soap, skin oils, hair, microorganisms, and cleaning chemicals. Agricultural runoff contains plant nutrients, fragments of roots, fungal spores, and compounds released by growing media. The International Space Station provides the most advanced working example of water recovery in orbit. In 2023, the American segment reached roughly 98% water recovery after new equipment began extracting additional water from the concentrated brine left behind by urine processing. That achievement means nearly all water entering the recovery system can eventually return for use. The system still depends on functioning pumps, filters, seals, heaters, sensors, and replacement components supplied from Earth. A generation ship would need to maintain the same basic processes for centuries. Distillation separates water by turning it into vapor and leaving many dissolved substances behind. Membranes can allow water molecules to pass, while blocking larger particles or certain dissolved compounds. Activated carbon traps many organic chemicals on a vast internal surface formed by microscopic pores. Ion exchange materials remove electrically charged contaminants such as calcium, nitrate, or some heavy metals. Catalytic oxidation uses heat and a catalyst, which is a material that helps a chemical reaction occur to break remaining organic compounds into simpler substances. No single method removes everything. Trace amounts of medicine can pass from patients into urine. Plastic tubing may release small additives into the water. Metal plumbing can contribute copper, nickel, or other elements. Cleaning products and agricultural chemicals may enter through spills too small to notice at the time. Microorganisms add another layer of complexity. Bacteria can grow inside pipes, tanks, and filters, especially where water moves slowly. Some produce thin communities called biofilms that attach firmly to surfaces and resist ordinary cleaning. Each trip around the loop gives contaminants another opportunity to remain behind. A harmless concentration during 1 year may become significant after repeated reuse unless the treatment system removes it faster than it accumulates. Filters and sorbent materials eventually fill. A sorbent is a substance that captures chemicals on its surface or within its structure. Some can be heated, washed, or chemically treated and returned to service. Others gradually lose performance and must be manufactured again. Water also disappears temporarily from the active loop. It may remain inside a growing tree, a container of stored food, damp agricultural material, medical supplies, or waste awaiting processing. A damaged compartment could trap thousands of liters behind a sealed bulkhead. Tiny losses matter over long periods. Losing 0.1% from a water inventory each year would remove close to 40% over 500 years if none of it were recovered later. The ship would therefore carry substantial reserves. Some would remain inside shielded tanks for drinking and emergencies. Additional water could absorb heat from machinery before carrying it toward the radiators. Tanks arranged around living areas would also help reduce radiation exposure. Emergency supplies must remain isolated from the main network. A biological contaminant or chemical spill inside the ordinary loop should never reach every available reserve. Direct human consumption would represent only part of the total demand. Large agricultural areas require water for nutrient circulation, crop growth, humidity control, and cleaning. Even when most of that supply returns, the volume moving through the farms could greatly exceed the amount poured into drinking cups. Across generations, the same molecules may move through thousands of bodies and countless harvests. That continuity gives the ship one of its greatest efficiencies, provided purification remains ahead of contamination and leakage. Clean water prepares the biological system for its largest daily task. The farms must turn light, minerals, and recycled waste into millions of calories without allowing one failed harvest to threaten the entire population. For a population of 1,000 people, food production would begin with a daily requirement of roughly 2 million to 2.5 million dietary calories. Individual needs would vary with age, body size, health, and physical activity. A technician performing heavy maintenance might require more energy than someone recovering in a hospital. Children would need changing amounts as they grew. Pregnancy, illness, and old age would each place different demands on the agricultural system. Stored food could provide protection during the early voyage and cover temporary harvest failures. It could never support a journey lasting several centuries. At 2,000 calories per person per day, 1,000 passengers would consume more than 700 million calories in a single year. Even dry grains, oils, and preserved foods would occupy enormous storage volumes across multiple generations. The ship would need to grow most of its food continuously. Potatoes and sweet potatoes could provide large amounts of carbohydrate from relatively compact growing areas. Wheat and rice would contribute grain, while soybeans and other legumes would supply protein and oils. Legumes also work with bacteria that convert nitrogen gas into chemical forms plants can use, although that relationship would need careful management inside a controlled habitat. Hydroponic systems could grow many crops without ordinary soil. Plant roots would sit in water containing measured amounts of nitrogen, phosphorus, potassium, and trace minerals. Sensors would track acidity, oxygen, temperature, and nutrient concentration. Aeroponic systems would suspend roots in enclosed chambers and spray them with a nutrient-rich mist. This can reduce water use and deliver oxygen efficiently to the roots. A blocked nozzle or failed pump could damage plants quickly, so aeroponic rooms would require backup equipment and close monitoring. Leafy crops such as lettuce, spinach, and kale could provide vitamins and fresh texture. Tomatoes, peppers, strawberries, and dwarf fruit plants would add dietary variety, though fruiting crops often require more space, time, and pollination than simple leaves or tubers. Light-emitting diode systems could direct useful wavelengths toward the plants. Chlorophyll absorbs strongly in red and blue regions of visible light, allowing lamps to emphasize colors that support photosynthesis. Electricity would still be required in large quantities. Almost all of the energy entering the lamps would eventually become heat that the ship's cooling system must remove. Some agricultural areas might use soil or manufactured soil-like material. A biologically active substrate can hold nutrients and support fungi, bacteria, and other organisms around plant roots. Those communities may help suppress disease and release minerals from organic waste. Their added complexity also makes them harder to control than a tank containing a known nutrient solution. Algae could grow in illuminated vessels, converting carbon dioxide into oxygen and edible biomass. Species such as spirulina contain substantial protein, though relying heavily on algae would create a narrow and repetitive diet. Algae would work better as one part of a broader food system. Protein could also come from aquaculture. Tilapia are often considered for controlled fish farming because they grow relatively quickly, tolerate a range of conditions, and can consume plant-based feed. Their tanks would produce nutrient-rich waste that could support crops after treatment. Insects require less space and feed than cattle or pigs. Mealworms or crickets could convert some plant material into protein, although waste chemistry, disease control, and public acceptance would matter. Chickens or rabbits might provide familiar foods, but they would consume crops that people could eat directly and would require veterinary care, housing, and additional water. Pollination would vary by crop. Workers could transfer pollen by hand using brushes. Small machines might vibrate flowers or move pollen through controlled air currents. Bees or other insects could handle larger areas, while adding another living population that might decline unexpectedly. No single farming method should support the entire ship. Agricultural districts could be divided by sealed doors, independent ventilation, and separate water loops. A fungal infection in one wheat room would then have less chance of reaching every grain crop. A pump failure in one hydroponic bay would leave other food pathways operating. Seed banks would preserve many varieties, but storage alone would provide limited protection. Seeds lose viability at different rates, even under cold and dry conditions. The crew would need to grow stored varieties periodically, collect fresh seed, and maintain active breeding programs. New strains might be selected for changing light conditions, altered microbes, or diseases that appeared during the voyage. Plant waste, uneaten food, human waste, and dead microorganisms would return to processing systems. Decomposers would release nitrogen, phosphorus, and other nutrients so they could enter the next harvest. Every meal would therefore emerge from a circulating network of light, water, minerals, organisms, and machinery. The farms would occupy some of the largest inhabited spaces aboard the vessel because they serve as food factories, atmospheric equipment, and living biological reserves. Their crops could be chosen with extraordinary care before departure. The bacteria, fungi, and viruses surrounding those crops would continue reproducing far faster than the people managing them. Beneath the crop leaves, the fastest changes aboard the ship would occur in places too small to see. Bacteria would live inside nutrient tanks, around plant roots, within human intestines, and across damp surfaces in the waste system. Fungi would break down dead plant material. Viruses would move through plant, animal, and microbial populations. Together, these organisms would perform much of the chemical work that keeps the farms productive. Some bacteria can divide in less than 1 hour when warmth, moisture, and nutrients are favorable. Escherichia coli, under ideal laboratory conditions, can reproduce in roughly 20 minutes. A single microbial lineage could therefore pass through thousands of generations during one human lifetime. Each division creates another opportunity for genetic change. Most mutations have little effect or make an organism less successful. A useful change can spread quickly when it helps a microbe consume a nutrient, tolerate a disinfectant, or reproduce in a newly available part of the habitat. Natural selection favors whatever allows the organism to leave more descendants under current conditions. The design stability of the ship has no special importance to that process. Many microbes would remain essential. Some bacteria convert nitrogen into forms that plants can absorb. Others release nutrients while decomposing roots, leaves, and human waste. Fungi can form partnerships with plant roots and help them gather minerals. Fermentation organisms could produce food, medicines, or industrial chemicals. These helpful communities can change through competition, contamination, mutation, or accidental sterilization. A cleaning procedure intended to remove one pathogen might also eliminate organisms that suppress it. A faster-growing strain could displace a slower one that performed a useful chemical function. A small change in temperature or acidity may favor an entirely different community. Returning one control panel to its original setting would not necessarily restore the earlier ecosystem. The organisms present after 100 years may differ from those carried aboard at launch. Biosphere 2 provided a smaller example of this kind of ecological reorganization. During its sealed missions in Arizona, many introduced pollinating insects disappeared. Ants and cockroaches became unusually successful, while fast-growing vines spread through parts of the enclosed environment. No designer had instructed those species to dominate. The conditions inside simply favored them. Crop disease could produce a more direct threat. Large agricultural systems often depend on plants that share similar genetics because uniform crops grow and ripen predictably. That similarity can also give a pathogen many vulnerable hosts. The Irish potato famine began in 1845, after the organism Phytophthora infestans spread through potato fields. It is commonly called a fungus, though it belongs to a separate group of fungus-like organisms known as water molds. The pathogen damaged leaves and caused tubers to rot. Many Irish farmers relied heavily on a small number of potato varieties. Once the disease reached those susceptible plants, it moved through fields with devastating speed. Crop failure continued across several seasons, contributing to mass hunger, disease, emigration, and approximately 1 million deaths. A generation ship would need several varieties of every major staple. Wheat, potatoes, rice, and soybeans should be divided into genetically distinct lines, so one disease cannot exploit the same weakness across the entire harvest. Wild relatives would provide additional protection. A wild potato from the Andes may produce smaller or less appealing tubers, while carrying resistance to a disease that defeats a high-yield cultivated variety. Plant breeders could cross those traits into future crops. Frozen seeds and genetic archives would preserve options, although living breeding programs would remain necessary. Stored material must be tested, grown, and renewed before age or equipment failure removes it. Helpful microbes would need archives of their own. Cultures could be frozen or dried and stored in separate shielded compartments. Scientists would compare those reference strains with organisms currently living in the farms. Microscopes could reveal changes in cell shape and population. Culturing samples would show which organisms still grow under known conditions. Chemical analysis could detect altered nutrient flows. Deoxyribonucleic acid sequencing would identify mutations and track the arrival of new strains. These diagnostic systems depend on sterile containers, reagents, sensors, computers, and trained technicians. Ecological monitoring therefore reaches back into the machinery and manufacturing clocks. A serious food decline would spread beyond the farms. Reduced calories, weakened physical work capacity, and immune function. Rationing increases tension within the population. Engineers and medical workers may be reassigned to emergency agriculture, allowing maintenance elsewhere to fall behind. The living systems aboard would continue adapting throughout the voyage. Some changes could make the ecosystem more resilient. Others could slowly turn useful organisms into competitors or pathogens. The human population would undergo its own generations of inheritance and change inside the same isolated vessel. How many people would need to enter the ship at departure? There is no single accepted number because different studies define survival in different ways. One model may ask whether a population can avoid severe inbreeding. Another may include epidemics, accidents, infertility, changing family sizes, and the need to preserve an entire technical civilization. Frederick Marin and Camille Beloufi explored this problem with a computer simulation called Heritage. The program followed imaginary crew members through births, deaths, relationships, and reproduction across many generations. In one widely reported experiment, an initial population of 98 people completed a simulated voyage, lasting about 6,300 years, without catastrophic inbreeding. Success depended on strict conditions. Reproduction was delayed during part of the journey. Family sizes were controlled according to the population's current needs. Pairings between close relatives were prevented, and the starting group was assumed to contain healthy genetic diversity. 98, therefore, represents a mathematical result inside a carefully managed model. It does not demonstrate that 98 people would form a safe or desirable generation ship society. A small community could be devastated by an ordinary sequence of events. Several people might be infertile. An accident could kill adults from one age group. A respiratory infection might spread through the ship before doctors understood it. If too few children were born during one decade, the population could later contain many older adults and too few workers to replace them. The number of people physically aboard is called the census population. Geneticists also use the term effective population, meaning the smaller group that actually passes its genes into future generations. A vessel might contain 500 people while only 200 regularly have children. Some families may have several descendants, while others have none. Unequal family sizes reduce effective population because more of the future population comes from a limited set of ancestors. Chance then has greater influence over which genetic variants survive. This process is called genetic drift. In a large population, one unusual variant can remain present in many unrelated families. In a small population, it may disappear after a few people die or become unusually common because one family has many children. A temporary population crash creates a bottleneck. Even if the community later grows again, much of its earlier diversity may already be lost. Related parents are more likely to carry copies of the same rare genetic variant. Some harmful variants are recessive, which means a person can carry one copy without becoming ill. A child receiving the same harmful version from both parents may develop the associated condition. As relatedness increases across generations, these pairings become more likely. Anthropologist Cameron Smith has argued for founding populations in the thousands, when broader genetic health and resilience are included. Some estimates begin around 7,500 people. More cautious proposals extend into the tens of thousands, allowing greater mate choice and protection against demographic shocks. A larger population would also preserve more professions. Several surgeons could train replacements. Different engineering teams could work independently. Schools could support specialized education, while political institutions would have enough people to contain genuine disagreement without dividing the entire community into a few families. Each additional person increases the ship's mass and resource demand. 10,000 passengers require roughly 10 times the food of 1,000, along with more housing, water processing, medical care, and radiation shielding. The genetically safer vessel becomes harder to accelerate between stars. Frozen genetic material could widen the biological population without adding thousands of living passengers at launch. Sperm, eggs, embryos, and tissue samples might be collected from a large donor group on Earth. Later generations could use that material to introduce variants no longer present among the living population. Cryopreservation keeps biological material at extremely low temperatures, so chemical activity slows almost to a halt. The storage system would need uninterrupted cooling, radiation protection, temperature monitoring, and several separated vaults. Fertility clinics, laboratory equipment, and trained medical teams would still be required centuries after departure. Its use would also require consent and public trust. Voluntary genetic counseling could help people understand inherited risks. Population planners might recommend certain pairings or encourage births during periods when the population is shrinking. Stronger control could restrict who may have children and when, giving a governing authority enormous power over private life. The founding population therefore determines more than genetic survival. It shapes family choice, medical burden, professional depth, and the amount of control later generations may face. Even a large and genetically diverse population will experience injuries, difficult births, chronic disease, and rare conditions. Every case must be treated with the people, medicines, and equipment already aboard. A child aboard the ship develops severe pain in the lower right side of the abdomen. The symptoms suggest appendicitis, an inflammation of the small pouch attached to the large intestine. On Earth, a hospital can confirm the diagnosis with imaging, consult a surgeon, test blood samples, and prepare an operating room within hours. Aboard the Generation ship, every part of that response must already exist inside the hull. The medical team would need an ultrasound scanner or another imaging system that still produces accurate results. Laboratory technicians would test for infection. A surgeon would require sterile instruments, reliable anesthesia, oxygen, monitoring equipment, and trained assistants. Recovery would depend on antibiotics, pain control, nursing care, and a clean room protected from resistant bacteria. Appendicitis is common enough for doctors to expect. Rarer conditions would be more difficult. A population of a few thousand people might support several general physicians, surgeons, dentists, pharmacists, mental health practitioners, and specialists in pregnancy and childbirth. It could not maintain the depth of expertise found across a large city. An unusual heart defect, neurological disorder, or complicated cancer might appear only once during a doctor's entire career aboard. Dental care would remain essential, because untreated infections can spread into the jaw or bloodstream. Pregnancy would require prenatal monitoring, emergency surgery, neonatal care, and treatment for conditions such as preeclampsia, which causes dangerous high blood pressure. Aging passengers would develop arthritis, cardiovascular disease, vision loss, and forms of dementia. Radiation exposure could increase the burden of cancer and circulatory disease. Doctors would need to detect tumors early, remove them when possible, and provide treatments without access to pharmaceutical factories or outside specialists. Medical equipment would age alongside the rest of the vessel. Imaging scanners depend on detectors, magnets, cooling systems, and computer controls. Laboratory analyzers require pumps, lamps, sensors, and chemical reagents. Sterilizers must reach precise temperatures and pressures. Ventilators contain valves and flow sensors that need calibration. A hospital may look complete, while one failed circuit board makes an important machine unusable. Medicines create a separate clock. Many tablets, injections, and sterile solutions have shelf lives measured in months or years. Heat, moisture, radiation, and chemical breakdown gradually reduce their strength or create unwanted products. A warehouse filled before launch could provide emergency reserves, though much of its original stock would be unsuitable after several decades. The ship would need to manufacture medicines continuously. Simpler drugs could be produced through chemical synthesis. Stored feedstocks, meaning basic chemical ingredients, would pass through controlled reactions before purification and testing. The process requires glassware, filters, solvents, temperature control, and instruments able to confirm that the final substance has the correct composition. Biological medicines are more demanding. Insulin, some vaccines, and many modern therapies are produced using living cells or microorganisms. Their manufacture requires sterile culture vessels, nutrient mixtures, purification equipment, and strict control of temperature and contamination. Vaccines may need to be updated if viruses or bacteria change during the voyage. Antibiotic resistance could develop as microbes reproduce under repeated exposure to the same drugs. A resistant strain inside a sealed habitat might spread through ventilation, water, surfaces, or direct contact before the medical team understood its behavior. The ship would encounter fewer infections introduced from outside. That isolation offers protection while increasing the consequences of any organism that escapes control. Quarantine rooms would need separate ventilation and waste handling because patients could never be evacuated to another hospital. Public health monitoring would therefore continue even during healthy periods. Technicians would sample air, water, food, and shared surfaces. Doctors would watch for clusters of fever, unusual coughs, digestive illness, or changes in skin infections. Early detection could prevent a small outbreak from moving through the entire population. Reproductive medicine would carry additional responsibility. If births are planned to maintain population size, doctors must track fertility and maternal health across generations. Cryopreserved sperm, eggs, or embryos would require specialists capable of using equipment built centuries earlier or replacing it with locally manufactured systems. Medical knowledge would need to reproduce itself as carefully as the population. Students would study anatomy, chemistry, microbiology, surgery, and diagnosis inside permanent medical schools. Clinical apprenticeships would place younger practitioners beside experienced doctors for years. Several people should understand every critical procedure so that retirement, illness, or an accident does not erase a medical capability. The hospital could contain an immense archive of recorded operations, diagnostic images, treatment manuals, and simulated patients. Those records would preserve information. Safe treatment would still depend on judgment developed through practice. A written procedure can describe where to make an incision. Experience tells a surgeon how tissue should feel when bleeding has become dangerous and when the expected diagnosis no longer fits the person on the table. That difference between stored information and living competence extends far beyond medicine. Every essential profession aboard the ship must be taught again before the people who understand it are gone. A complete digital archive might seem like the simplest way to protect the ship's knowledge. The vessel could carry textbooks, engineering drawings, medical images, repair videos, software, and simulations of every important system. Modern storage can hold libraries that once filled buildings. Copies could be distributed through shielded compartments, so one accident did not erase everything. The archive would need constant care. Radiation can flip bits inside electronic memory. Heat and age slowly damage storage media. File formats become difficult to open when the software that created them disappears. A diagram may survive perfectly, while the program needed to read it no longer runs on any working computer. The crew could protect records with error checking. A checksum is a small mathematical value calculated from a file. When the file is checked later, a changed checksum reveals that some data has been altered. Error-correcting systems can reconstruct limited damage when enough duplicate information remains. Several storage methods would add protection. Solid-state memory, magnetic media, optical disks, and printed records fail in different ways. Important archives would be copied onto newer equipment repeatedly rather than left untouched for centuries. Preserving information solves only part of the problem. An experienced technician may hear a faint change in a pump before any alarm appears. The pitch could rise as a bearing loses lubrication. A vibration felt through a handrail may reveal that a shaft has moved slightly out of alignment. A sweet chemical smell might suggest overheating insulation. These observations belong to tacit knowledge, meaning skill learned through practice that is difficult to capture fully in words. Manuals can list safe temperatures and vibration limits. Years of supervised work teach someone which small changes deserve immediate attention. The same principle applies in medicine, agriculture, machining, and laboratory work. A plant pathologist learns to distinguish nutrient stress from infection by the pattern across a leaf. A machinist feels when a cutting tool begins to chatter against metal. A surgeon recognizes when living tissue differs from the image shown in a training model. Apprenticeship transfers these abilities through observation, repetition, correction, and gradually increasing responsibility. The ship would need permanent schools, trade programs, laboratories, and clinical training. Children would learn ordinary language, mathematics, science, and history. Older students would enter long professional paths connected to the vessel's needs. Some roles could not be left entirely to popularity. A small society may produce many students interested in art or biology during one decade, and too few willing to study reactor maintenance. Education planners would need to predict retirements years ahead and ensure that critical professions always had replacements in training. Knowledge should overlap between people. One specialist in atmospheric chemistry creates a dangerous point of failure. Several people should understand the field, while nearby disciplines retain enough knowledge to assist during an emergency. History shows that technical practices can disappear even when fragments of written information survive. Roman builders produced structures using mixtures of lime, volcanic ash, stone, and water. Some marine concrete hardened through chemical reactions that continued after construction. Later, European societies still built with stone and mortar, yet many Roman supply networks, institutions, and large-scale construction practices were no longer available after the empire changed. The loss came through disrupted communities, trade, labor organization, and teaching traditions. A generation ship could experience a smaller version after an epidemic, political crisis, or long period of neglected education. One broken generation may be enough. If no apprentice learns to rebuild a certain power converter before the last expert dies, the archive may preserve every drawing while the practical chain has already ended. Crews must also reason from first principles. This means returning to basic physical laws when old instructions no longer match the ship. A repair manual written before launch may describe a factory tool replaced 2 centuries later. Engineers would need to understand why the component works, so they could design a new method using the equipment still available. Artificial intelligence could tutor students, compare sensor patterns, and guide medical diagnosis. Its processors, cameras, databases, and software would remain part of the same maintenance system. An artificial teacher becomes less useful when damaged sensors feed it unreliable information or its models no longer reflect the altered ship. Knowledge survives through people who study it, practice it, question it, and pass it forward with care. A generation may understand every reason the mission was designed as it was. That understanding cannot guarantee that its members will continue accepting a destination chosen centuries before their birth. The first people aboard would carry memories no later generation could fully inherit. They would remember natural wind, changing clouds, distant mountains, and the weight of rain falling from an open sky. They would also remember choosing the voyage. Every confined room and demanding maintenance shift would remain connected to a decision they had made for themselves. Near the end of the crossing, the arrival generation would gain a different source of meaning. The destination star would grow brighter against the background. Telescopes would begin resolving planets, moons, atmospheric gases, and weather patterns with increasing detail. Children might grow up knowing that they could become the first people to enter a new planetary system. The middle generations would live between those anchors. They would have no personal memory of Earth. Arrival might remain 200 years away. A person could spend an entire life maintaining water pumps, teaching reactor physics, or protecting seed collections without seeing either the beginning or completion of the mission. This position does not guarantee despair. Children born aboard may regard the ship as their natural home because it supplies every landscape and social experience they have ever known. A curved interior containing forests, streams, homes, and workshops could feel complete to someone with no memory of a planetary horizon. The strain would come from limited control and permanent confinement. Research from Antarctic stations offers a partial comparison. During the polar winter, crews may remain isolated for months while darkness, severe cold, and dangerous travel conditions restrict movement outside. Studies have reported disrupted sleep, irritability, low mood, reduced concentration, and slower thinking among some winter-over personnel. Submarine crews also live in enclosed spaces with limited privacy. Their sleeping areas may be only a few steps from machinery, workstations, and other crew members. They operate under strict schedules and cannot simply walk outside when conflict develops. Long space missions provide another useful reference. Russian physician Valery Polyakov spent approximately 437 continuous days aboard the Mir space station from 1994 into 1995. Scott Kelly and Mikhail Kornienko each spent about 340 days aboard the International Space Station during a mission ending in 2016. These records remain tiny compared with one human lifetime aboard a generation ship. Every person in an Antarctic station, submarine, or orbital laboratory expects eventual return. They also remain connected to governments, families, engineers, and medical experts outside their immediate habitat. The generation ship weakens both protections. Communication with Earth becomes slower as distance grows. A message sent from 1 light year away takes 1 year to arrive, followed by another year for the reply. At 4 light years, a complete exchange requires at least 8 years. At 10 light years, a person asking for advice might wait 20 years to receive an answer. Eventually, communication becomes an exchange of archives rather than conversation. News from Earth would describe events that were already years or decades old when the ship received them. The people who recorded a message might no longer be alive when the reply arrived. Interior design could reduce some of the psychological burden. Large agricultural districts would provide vegetation, moisture, changing smells, and living textures. Long sightlines could prevent every room from feeling enclosed. Water features might add sound and reflected light. Circadian lighting would imitate the daily changes that regulate sleep and hormone cycles. Artificial seasons could vary temperature, day length, crop colors, and public activity. Controlled rain might fall over some planted areas, while other districts remain dry. Private living space would be essential. A person needs some control over noise, light, visitors, and personal belongings. Even a small room with a closing door can provide relief inside a community where permanent escape is impossible. Art, sport, education, and public events would create experiences unrelated to maintenance. Parks could be redesigned over time, so one generation did not inherit every interior exactly as the founders left it. People might build new neighborhoods, change local customs, and develop forms of music shaped by the acoustics of the rotating habitat. These measures improve variation, belonging, and personal control. They cannot remove the central fact that every relationship continues inside a finite vessel. A serious disagreement cannot be solved by moving to another country. An unpopular leader remains connected to the same air and water systems as everyone else. Families involved in a long conflict may continue living only a few kilometers apart. The middle generations would therefore need more than endurance. They would need institutions capable of resolving conflict while preserving freedom, essential work, and trust. Once departure is only history and arrival remains beyond a lifetime, authority can no longer rest on the founder's original decision. The people currently alive must decide who controls the mission and what obligations anyone aboard can legitimately be required to carry. 200 years after departure, a council aboard the ship might face a proposal that the founders never anticipated. A newly detected planet in a nearby system appears more promising than the original destination. Reaching it would require a course change and perhaps another century of travel. Some residents support the change. Others argue that their ancestors built the vessel for a specific world and that altering the mission would betray generations of sacrifice. By then, everyone involved would have been born aboard. None would have agreed personally to the voyage. A workable political system would need to separate rules required for immediate survival from choices that remain open to public debate. No resident could claim private ownership of an oxygen processor and switch it off during a dispute. Water reservoirs, reactor controls, agricultural systems, and the pressure hull affect every person aboard. Damage to one shared system could spread through the entire population. Personal life still requires boundaries. People would need secure homes, private relationships, possessions, creative freedom, and protection from unreasonable surveillance. The ship cannot preserve itself by treating every individual as a replaceable machine component. The law would also need to handle familiar human problems under unfamiliar conditions. Theft might involve food, equipment, medicine, or access to restricted data. Negligence could damage a water loop or expose a district to radiation. Deliberate sabotage might place thousands of lives at risk. Violence, mental illness, and impaired judgment would continue to exist inside a population selected with great care. Exile would rarely be possible. Sending someone outside the hull would mean death, unless another habitat or vessel existed nearby. Long prison sentences would consume housing, food, medical care, and staff, while removing a person from the limited workforce. Restorative justice could resolve some offenses by repairing harm, requiring treatment, or returning the person to useful participation. Rehabilitation would have practical value because the community cannot easily discard people. Some individuals may remain dangerous despite treatment. Secure separation would still be necessary, supported by medical review and legal safeguards. A small population could not afford a justice system based entirely on either punishment or trust. Emergency authority creates a separate risk. During a hull breach, fire, epidemic, or reactor failure, decisions may need to be made within minutes. Commanders might seal compartments, impose quarantine, ration power, or order people into hazardous work areas. A constitution could permit temporary emergency powers, with clear limits, automatic review, and a defined endpoint. Without those limits, emergency government could become permanent. A leadership group might justify censorship or forced labor by claiming that the mission is always in danger. Reproduction would produce some of the hardest conflicts. Medical teams may calculate that the population needs more births during one decade and fewer during another. Genetic counselors could identify pairings that reduce inherited risk. Advice can remain voluntary. Stronger intervention could restrict pregnancy, assign reproductive priority, or pressure families to have children for demographic reasons. A rule designed to protect the population could enter the most private area of a person's life. The living community may also disagree about the destination itself. People could vote to slow the vessel and turn it into a permanent habitat. Separate districts might request greater independence. A large rotating ship could divide into semi-autonomous communities that manage schools, culture, and local law, while sharing power, air, and navigation. In 1620, passengers aboard the Mayflower signed a compact before establishing their settlement in North America. The document created a basic agreement for self-government among people facing uncertain conditions far from familiar authority. Its circumstances were brief and historically specific, yet it offers one limited reminder. A voyage can force people to define political legitimacy before arrival. A generation ship would need a far more durable arrangement. A layered constitution could protect essential life support systems and basic individual rights from ordinary political change. Other laws could be revised as technology, population, and culture evolved. Courts or review councils might prevent a temporary majority from damaging systems required by future generations. Permanent control by the founders would deny later generations meaningful consent. Unrestricted majority rule could allow one frightened election to dismantle safeguards that took centuries to build. Stability would depend on institutions able to preserve continuity while remaining answerable to the people currently alive. The mission would fail morally long before the engines stopped if its descendants came to see themselves as property belonging to an ancient plan. Law can organize behavior and resolve conflict. Centuries of maintenance require something deeper, a culture that gives ordinary life aboard the ship enough meaning to deserve preservation. A constitution can define who holds authority, yet its words will pass through generations whose language, customs, and priorities continue changing. English spoken 1,000 years ago would be largely unintelligible to most English speakers today. The opening lines of the Old English poem Beowulf, written down around the year 1000, require translation even though they belong to the same language family used across much of the modern world. A generation ship traveling for several centuries would experience its own shifts in pronunciation, vocabulary, humor, and social meaning. Technical language might remain more stable because machinery demands precise terms. Everyday speech could change much faster. This creates a quiet danger for records written near departure. A sentence that seemed clear to the founders may be interpreted differently 300 years later. legal definitions can drift. Instructions may survive while the cultural assumptions behind them disappear. Archives would need to preserve more than engineering manuals. Original recordings could show oceans, forests, cities, storms, and animals that no living passenger had ever encountered. Spoken languages should be stored with pronunciation guides and historical context. Scientific records would preserve how the mission was designed, while diaries and ordinary family videos would reveal how people actually lived before launch. Earth's meaning would still change. The founders would remember it as a physical place where they had walked and worked. Their grandchildren might know it through family stories. Several centuries later, Earth could become a symbolic origin, discussed with the same emotional distance that people today feel toward an ancestral homeland they have never visited. The destination would remain abstract for much of the crossing. It might appear in telescope images as a point of light accompanied by graphs showing temperature, mass, and atmospheric gases. Only during the final decades would planets become visible worlds with clouds, seasons, and recognizable geography. Culture would have to create meaning during the long interval between those two places. Launch anniversaries could mark another completed year of travel. Ceremonies might recognize the first harvest from a new crop variety or the reopening of a repaired habitat. Births and deaths would connect individual lives to the larger history of the vessel. Communication milestones could become major public events. When the ship crossed 1 light year from Earth, every reply from home would require at least 2 years. Farther out, the final real-time conversation would already belong to history. Communities might gather when delayed messages arrived, knowing that the speakers on the recording had aged or died during transmission. Daily life would need meaning beyond commemoration. Music, theater, gardens, competitive games, visual art, and literature would give people experiences unrelated to emergency readiness. Sports played in rotating gravity might develop rules unique to the curved habitat. A ball thrown high above the floor would appear to bend because of the ship's rotation, allowing games that could never exist on Earth. Neighborhoods would change their architecture over time. One district might prefer dense housing around public gardens. Another could build quieter residential areas beside agricultural land. Clothing, food, celebrations, and family customs would begin reflecting local history aboard the ship. Trying to freeze the founders' culture would eventually make ordinary change feel like disobedience. It could also preserve customs that later generations found irrelevant or harmful. Cultural continuity would work better by protecting shared competence, historical memory, and the value of cooperation while allowing new forms of life to emerge. A society centered entirely on duty could exhaust its population. Children raised only to replace retiring technicians may come to view education as an obligation imposed by the dead. A society that treats maintenance as unimportant could lose the technical discipline keeping its air and water safe. The durable balance would allow people to build meaningful lives while understanding which forms of work protect everyone around them. Semi-autonomous districts could support different educational methods, ceremonies, and family structures. Shared technical standards would still govern electrical connections, pressure seals, emergency signals, and medical records. Cultural variety could grow without making the physical ship incompatible with itself. A fleet would offer even greater separation. Several vessels traveling within communication and navigation range could develop distinct identities while trading knowledge, seeds, equipment, and trained workers. People might migrate between ships during scheduled transfers. Physical distance would also distribute risk. One epidemic, political collapse, fire, or major impact would be less likely to end the entire mission when the population occupied several independent habitats. The vessels would still need a shared language for navigation and emergency coordination. Common docking systems and compatible equipment would allow mutual assistance across generations. Culture becomes part of the survival architecture through these connections. It gives people reasons to learn difficult skills, cooperate with neighbors, raise children, and preserve institutions whose benefits may not become visible for decades. A generation ship remains socially alive when its inhabitants can create worthwhile lives in the present, while carrying enough knowledge and discipline into the future. Each survival clock has now been followed separately. Their greatest danger appears when damage to one system begins accelerating decline throughout the rest. A decline aboard the ship might begin with an ordinary agricultural report. Wheat production has fallen by 6% over 2 harvests. Potato plants are developing smaller tubers, and one soybean room is recovering slowly from a fungal outbreak. The population still has enough food, though stored reserves are now being opened more often than planned. Nutrition officers reduce daily portions by 150 calories, while biologists search for the cause. That change sounds modest. Across 1,000 people, it removes 150,000 calories every day. Workers performing heavy repairs begin tiring earlier during their shifts. Recovery from illness slows. Arguments over meal allocation become more common because some departments claim their work requires larger portions. Agricultural specialists receive additional staff, drawing technicians away from water treatment and machinery inspection. Scheduled maintenance on several pumps is delayed by 3 weeks. One of those pumps later develops excessive vibration. Its failure interrupts nutrient flow through another crop room, reducing the harvest that was meant to replace the original loss. The agricultural clock has now accelerated the machinery clock. Reduced food production lowered labor capacity, which delayed maintenance, which damaged food production again. This is a feedback loop. The result of one problem strengthens the conditions that caused it. A second cascade could begin in the power system. Suppose one reactor shuts down after metal fragments appear in its coolant. Backup reactors carry the electrical load, but the ship has less reserve capacity. Agricultural lighting is reduced by 5%. Some manufacturing furnaces operate only during off-peak hours, while water treatment equipment runs closer to its minimum safe rate. Hospitals postpone energy-intensive procedures that can safely wait. Cooling systems allow equipment rooms to become slightly warmer. Electronic components age faster at elevated temperatures, increasing the chance of future failures. The backup systems are still working, yet the ship has consumed part of the margin that once protected it. Redundancy only provides strong protection when the backup systems can fail independently. 2 reactors connected to the same coolant loop remain vulnerable to one rupture or contaminated fluid supply. Several computers may appear independent, while sharing identical power converters from the same defective production batch. This is called common cause failure. One event defeats several systems that were expected to protect one another. Spare components create another form of safety margin. The first failed valve can be replaced immediately. Later replacements reduce the inventory until only locally manufactured versions remain. Backup habitats may be opened after a fire or contamination event, leaving fewer sealed areas available for the next emergency. Each successful recovery can therefore leave the ship slightly less protected than before. Sociologist Diane Vaughan used the phrase normalization of deviance while studying organizational decisions surrounding the Space Shuttle Challenger disaster in 1986. The idea describes a process in which an unusual or degraded condition gradually becomes accepted because it has not yet produced a catastrophe. A pump operating 10 degrees above its original limit may be tolerated after repeated inspections find no visible damage. Lower crop yields can become the new planning baseline. A district that once maintained 4 independent oxygen sensors may learn to function with 2. Later generations may never remember the original performance. They compare the ship with the already diminished vessel they inherited. Calculating one exact probability of survival would give a false sense of precision. Multiplying estimated failure percentages for reactors, farms, and social institutions cannot capture the way those systems affect one another. A more useful model compares 2 changing rates. The failure rate measures how quickly new problems appear. The repair rate measures how quickly the population can diagnose those problems and restore lost capability. Early in the voyage, the repair rate may remain comfortably higher. Technicians are numerous, machinery is young, and warehouses contain original spare parts. A broken component is replaced before the next serious fault develops. Centuries later, failures arrive more frequently. Materials have aged, reserves have declined, and some technical knowledge has narrowed. Repair work takes longer because replacement parts require local manufacture and older systems no longer match their original plans. Eventually, the 2 rates can cross. Beyond that point, crews still complete repairs every day. The unresolved backlog continues growing because new failures appear faster than old ones can be corrected. Inspection intervals lengthen. Temporary solutions remain in place. Remaining backups are consumed one by one. The vessel may continue to look inhabited and orderly throughout this decline. Lights remain visible through its windows, children attend school, and crops continue growing in most compartments. Its safety margin is disappearing faster than the people aboard can restore it. How soon that crossover arrives depends heavily on the voyage's duration. 100 years exposes the ship to a very different number of component cycles, harvests, births, and institutional transfers than 500 or 1,000 years. Duration now becomes the clearest way to describe the ship's chances. There is no universal expiration date for a generation ship. Survival depends on its population, cruising speed, shielding, manufacturing capacity, destination, political stability, and the amount of redundancy built into every essential system. Chance also matters. A vessel may avoid major impacts and epidemics, while an identical ship could experience both during its first century. The most responsible answer is therefore a range of increasing risk. A voyage lasting roughly 100 years could overlap 2 to 4 human generations, depending on when passengers have children. Some people born near departure might live long enough to meet descendants who expect to witness arrival. 1 century remains far beyond any demonstrated closed human ecosystem. Biosphere 2's first sealed mission lasted 2 years. The International Space Station depends on continuing deliveries, replacement equipment, and extensive support from the ground. Even so, a century-long vessel could begin with large inventories of electronics, medicines, filters, and precision components. Many original structures might remain in service through careful inspection and refurbishment. Institutions would need to transfer leadership several times, while the founding purpose could remain within living family memory. The ship would still face radiation, ecological drift, machinery failure, and social conflict, though fewer complete renewal cycles would be required. A 200-year journey moves deeper into unfamiliar territory. Original reactors, medical equipment, computer systems, and manufacturing tools would almost certainly require extensive replacement. Children born near the middle of the voyage would inherit a mission whose departure they knew only through records. This general duration remains within serious conceptual study. Project Hyperion used a voyage of approximately 250 years as the basis for its generation ship design challenge. Teams had to combine artificial gravity, architecture, life support, social organization, and knowledge transfer within one coherent vessel. The challenge recognized that a ship's physical structure and its civilization must be designed together. The winning concept, called Chrysalis, proposed an enormous rotating cylindrical habitat. Public descriptions placed it at roughly 58 kilometers in length, with a population of several thousand people and a journey lasting about 400 years. Its design included agricultural regions, residential districts, industrial capacity, radiation protection, and spaces intended to support psychological health. Those figures describe a conceptual study rather than tested engineering. No structure remotely comparable to Chrysalis has been built, and no closed ecosystem has been operated at its proposed scale. Around 500 years, the survival clocks begin entering more speculative territory. A component lasting 50 years must be replaced roughly 10 times. Reactor systems may undergo several major rebuilding cycles. Medical schools must recreate specialist knowledge through many generations. Crop varieties, useful microbes, and stored genetic material require repeated testing and renewal. The population would also rebuild its political legitimacy more than once. Languages could shift. Districts could develop separate identities, and the original destination might lose meaning before it became visible as a world. Material fatigue, ecological stability, cultural continuity, and industrial self-replication become major unknowns at this scale. Humanity has no direct evidence showing that all four can remain healthy together for 5 centuries. A 1,000-year crossing would include approximately 30 to 40 human generations. No experiment has maintained a sealed human ecosystem for even 1% of that duration. A millennium-long vessel would need to reproduce machine tools, electronics, pharmaceuticals, sensors, and precision instruments many times. Its inhabitants would have to preserve scientific reasoning through epidemics, demographic changes, political disputes, and periods of declining resources. Several design strategies could extend the survival envelope. Modular habitats would allow damaged or contaminated sections to be sealed without abandoning the entire vessel. A fleet could divide the population among several ships, reducing the chance that one collision, disease outbreak, or political collapse ends the mission. Genetic archives could restore biological diversity after a population bottleneck. Autonomous monitoring systems might detect changes in crop chemistry, structural vibration, or human health before symptoms became obvious. Their sensors and processors would still require maintenance, so automation would extend human capability rather than remove the underlying dependency. Each safeguard pushes the most dangerous crossover farther into the future. Cumulative damage continues beneath it. 1 to 2 centuries, therefore, appear extraordinarily difficult, while remaining within the range of detailed scientific and engineering speculation. Voyages lasting several centuries depend increasingly on renewal systems humanity has never demonstrated. A journey approaching 1,000 years lies beyond what present science can describe as reasonably reliable. A generation ship might survive for centuries. Current evidence offers no reason to assume that a healthy technological civilization could remain sealed indefinitely. The crossing also has a final demand. The vessel must reach the destination with functioning engines, healthy people, usable factories, and enough remaining capacity to slow down and begin again. Centuries after departure, the destination star would begin to look different. For most of the voyage, it would remain one point among thousands. During the final years, its light would strengthen. Onboard telescopes would begin separating nearby planets from the glare. Spectrometers would study their atmospheres by measuring which wavelengths of light were absorbed by gases such as water, vapor, carbon dioxide, methane, or oxygen. The ship would still be moving at interstellar speed. A vessel traveling at several percent of light speed cannot arrive and simply enter orbit. At 3% of light speed, it moves about 9,000 kilometers every second. Without deceleration, it would cross the planetary system in a matter of days and continue into interstellar space. Slowing down requires the ship to remove the enormous kinetic energy accumulated during acceleration. One approach would reserve fuel for a long reverse burn, turning the propulsion system toward the direction of travel and firing it for months or years. That plan assumes the engines remain functional after centuries of radiation, vibration, maintenance, and replacement. Fuel must survive the entire crossing without being consumed during earlier emergencies. Navigation instruments must point the vessel accurately enough to avoid wasting the final reserve. Magnetic sails have also been proposed. A magnetic sail would create a vast magnetic field using superconducting loops. Charged particles in the interstellar medium or the destination star's wind would push against that field and gradually slow the ship. The concept could reduce the amount of propellant carried for deceleration. It depends on enormous lightweight superconducting structures operating reliably in deep space, and no system of the required size has been tested. Gravitational assists around planets or stars might remove some velocity. They work only after the vessel has entered the system on a precise path and slowed enough for local gravity to redirect it safely. Arrival would also reveal how much the destination had changed since launch. The observations used to choose the planet may be 200 or 500 years old. Stars pass through activity cycles. Planetary climates shift. Volcanic eruptions can alter atmospheric chemistry, while impacts may change a surface within a much shorter time. Remote observations from Earth cannot provide every important detail. A planet inside the conventional habitable zone may have surface temperatures that permit liquid water under certain conditions. Its atmosphere could still be too thin, too dense, or chemically harmful. Gravity might weaken human bodies or place excessive strain on them. The star may produce damaging flares, and native biology could create hazards that no distant telescope could identify. The ship would need working probes during its final approach. Robotic craft could enter orbit, sample the atmosphere, map radiation, and examine possible landing sites. Laboratories aboard the main vessel would analyze those results before anyone descended. The generation ship may remain in orbit for years, while the population learns what kind of world it has reached. A difficult planet could keep the vessel functioning as a permanent settlement for decades. If conditions prove unsuitable, the ship itself may become the destination. Arrival, therefore, demands far more than living passengers. The power system must retain enough surplus for deceleration, exploration, and settlement. Machinery must still hold the precision required to operate probes and construct new equipment. The hull and shielding must protect the population during an uncertain transition. Agriculture must continue feeding everyone while landing plans change. The population needs enough health and genetic diversity to establish a durable community. Technical knowledge must be broad enough to interpret an unfamiliar planetary system. Society must make decisions no founder could settle in advance. People may disagree about landing, remaining in orbit, or dividing between several habitats. Political cooperation during these final choices becomes part of the mission's surviving capability. A carefully designed generation ship might conceivably endure a journey lasting 1 to several centuries. No existing experiment proves that a sealed technological civilization can remain healthy for that long. A voyage approaching 1,000 years requires repeated renewal of ecosystems, factories, medical systems, professional knowledge, and political institutions. Humanity has never demonstrated those abilities together, across even a small fraction of that time. Faster propulsion improves every survival clock by reducing the number of harvests, component cycles, births, repairs, and transfers of authority required before arrival. The people approaching the new star would be descendants of passengers who accepted that they would never see it. Their arrival would depend on millions of ordinary actions performed across generations. A bearing replaced before it failed. A child taught a difficult skill. A crop protected from disease. And a conflict resolved without damaging the systems everyone shared. Beyond the windows, the giant cylinder would still appear warm against the dark. Its deepest danger was never limited to one spectacular accident. The journey ends when one essential capability can no longer be repaired, regrown, reproduced, taught, or trusted. A generation ship may survive deep space for centuries. Greater distances place its future in the hands of abilities no civilization has yet proven it can preserve. The most realistic path to another star may require a vessel capable of carrying an entire world and an engine fast enough that the world does not have to remain sealed forever.